Hi, my name is Tonatiuh Matos. I will speak about the cosmology from quantum fluctuation of space-time. Well, the idea is very simple. As you know, general relativity is formulated on a space-time, where the space-time is a four-dimensional differential manifold. This is something like this square here locally. Well, but if the gravitational field is a quantum field, as we think, well, then the space-time should be more something like this here, this lake, because the quantum fluctuations uh, have a different way, different waves in the space-time. And that's it, this one are the quantum fluctuations space-time. Well, then the idea in this talk is to introduce these quantum fluctuations into the Einstein equations. And with these new Einstein equations, we can formulate cosmology and compare them with observations. Well, then in order to do so, let me you remind um, the case of the photon. As you know, the energy of a photon is given by this formula, where h is the Planck constant and nu is the frequency of the photon, and the energy is given by the h times nu. Of course, we can associate to this energy virtual mass given by this Einstein's formula. This mass is virtual because the mass of the photon continues being equal to 0. Well, if we can associate to this frequency, to this mass, a wavelength given by the Compton wavelength given in this formula. You see, this is real, this lambda is real, while the mass is virtual mass. Well, the same is happening with graviton. Graviton is for us the the interaction of the of the gravitational field, the particle of the interaction of particle field. Well, the mass of this graviton is equal to 0, and we have again that the energy is given by the h times the frequency, and we can associate to them mass, virtual mass, and we can relate them with the wavelength of the Compton wavelength given by this formula in the exactly the same way as in the case of photons. Well, with this in mind, we what we are going to do now is to introduce this energy into the Einstein equations, because everything gravitates, and this energy is something what we have to take into account in the space-time in the universe. Well, how to do that? Well, we can go in the following way. As you know, the weak field limit of the gravitational field is given by this formula, where g mu nu is the metric, is the space-time metric, eta mu nu is the Minkowski metric, and h mu nu is a perturbation, a small perturbation of the Einstein equations, and in the sense that h to the square is almost equal to 0. The Ricci tensor is given in this way as the D'Alembertian, 1/2 of the D'Alembertian of the h mu nu. But because the eta mu nu is a constant, is the Minkowski metric, then we can put this rel mu nu equal to the D'Alembertian of the k mu nu without loss of generality. Well, as we know, the scalar field without massless scalar field formula is the Lambertian equal to 0. But if the scalar field has a mass, then we have to add this term, m squared c squared over h bar square times the scalar field, where h bar is the Planck constant divided by 2 pi. Well, in the case of a vector field, electromagnetic field, it's exactly the same. You have the Lambertian of the if the electromagnetic field is massless, then the Lambertian is equal to 0. But if this electromagnetic field has a mass, then we have to add this term in exactly the same way. Well, what we are going to do is that exactly the same. As you know, the gravitational waves or the graviton has this formula. The Lambertian of g mu nu is equal to 0. But if this g mu nu has a mass, then we have to add this term, and this is what we are going to do. Well, then this is for the weak limit. Of course, for the general equations, we have to do that in the same sense, and this is what they are going to do. Well, this is the Einstein equations. We can rewrite the Einstein equations in this way, and without loss of without sources, what we have is this equation. Well, this is the equation what we are going to take into account. Well, we remind again the weak field limit. Remember that the R mu nu is equal to the Lambertian of g mu nu. Well, and we compare that with the Einstein equations, and if we put 2m equal to m squared c squared over h bar squared, then these two equations are exactly the same. Of course, m is a virtual mass, and we have to work with real things, and therefore we use again the Compton mass formula, the Compton wavelength, and we put the m in terms of the Compton wavelength, and what we obtain is that the m is equal to 2 pi squared over lambda squared, where lambda is the wavelength, the Compton wavelength of the graviton, of the graviton. Well, okay, then there is a problem because the universe is expanding, and therefore the lambda, the wavelength of the graviton, is growing up. For example, at the beginning of the universe, you have a size, and then after a while, this wavelength is growing up, and growing up all the time at the speed of light. And everything that grows or goes to the speed of light follows this formula given here in the bottom. And if we use that for give the velocity of growing or growth of the graviton, then we have to write the lambda in terms of the SDSRH parameter that is unitless. Well, we can rewrite this equation in terms of the n-fold coordinates, and you have this formula. Well, the CMaDE model, this means the Compton mass dark energy model, is given in the following way. The Einstein equations are then added with this new term where m, where this m is 2 pi square of lambda square, and the lambda is the Compton wavelength of the graviton, and is growing up to the velocity of light given by this formula here. This is the CMaDE model, and this is what we are going to study. Well, then the next step is to find the, of course, the Friedmann equations in order to study the cosmology. These equations can be rewritten in this way, where the omega m is the rate of this quantity given by these formulas. And of course, the Einstein equations are very, very similar to the lambda cold dark matter equations, but we have some differences. The first difference is the equation for the dark matter. You see, the dark matter is interacting with the quantum fluctuation of the space-time. But we don't know the nature of dark matter, and we don't know how much matter or with much energy is are interchanging between the dark matter and the quantum fluctuations. And therefore, it is convenient to put here a bias parameter in order to measure this interaction. In the same way, we have here the bottom equation, and this is the equation for the quantum fluctuations of dark matter. sorry, of the quantum fluctuation of the universe, and we don't know how much of this energy is used for the expansion of the universe, because you have a formation of black holes or a large scale structure of the universe, and therefore it is convenient to put another bias parameter in order to measure how much of this energy is for the expansion, accelerated expansion of the universe. Well, then we start with these equations. We can solve them numerically. It is very, very easy. And we see here the comparison between the CMaDE model and the lambda Calder matter model. And you see they are really very, very similar. The difference is very small. It's less than 7%. And they are identical before recombination. You see here. Well, then we use again these Friedman equations, and now we compare them with observations. Of course, the main observations are very well known, and we start with the cosmic censors, baryon acoustic oscillations, and the supernovae from Pantheon. And the surprise is that we find that the delta chi² is equal to 3.25 in favor of the CMaDE model against the lambda Calder matter model. That means that the CMaDE model explains better the observations of the cosmic censors, BAO and Pantheon, in comparison with lambda Calder matter, with the following parameters. The Hubble parameter is equal to 0.69. The matter contents is 31% of the universe, of the matter of the universe, and the curvature is 0.08. Well, then we make the same for the cosmic microwave background radiation and the mass power spectrum using the class code, and we find exactly the same. They are very, very well in agreement with the observations. And now the H, that means the Hubble parameter is equal to 0.68 in comparison with the last one is 69. And the baryons are 4.8% in the universe. Dark matter is 23% of the universe, and the curvature is 0.001. They in very, very good agreement with the previous observations. That means that we have a conclusion, and the conclusion is very simple. Quantum fluctuation in space-time seem to be able to explain very well the accelerating expansion of the universe without the need of a cosmological constant, exotic extra matter, or modifications to Einstein equations. we know that we need to further study this model because we have much to do, but so far this model is in very good agreement with the main observations of the universe. Thank you very much.